Alrighty, welcome back to Maths Methods. So we're going to have a quick chat about some maximum and minimum problems. Often you'll be given real life examples that require things to either be maximized or minimized. In particular, when you want to manufacture things, or if you're using fuel and things like that, you want to keep costs down. So you're looking at minimizing those costs. On the other hand, there's scenarios where you want to maximize things, and they're suggesting here often when you are selling things, you want to create the maximum profit. And they're suggesting here as well, if you wanted to organize a concert, you'd want the maximum amount of people to be able to attend. So they're saying, hey, we can use calculus to be able to solve these things. So I'm just going to have a look, pick out a few of these examples and have a bit of a chat about them. So the first one here, it says here, a farmer has sufficient fencing to make a rectangular pen of perimeter 200 meters. What dimensions will give an enclosure of maximum area? So again, just consider the following. I'll write it on here, with the text box. If we're dealing with a rectangle that has a perimeter of 200, remember, perimeter is going to be the same as you've got two lengths, and you've also got two widths, to create the rectangle. So you've got a length, a width, a length, a width, and in this particular case it's going to be 200. Now, we can rearrange things in this particular case. We can move the width over to the other side. 200 take away 2w is going to be equal to 2l. Fairly happy there. Then you could divide both sides by 2. When you end up with 100, take away w is equal to l. Yep. So what they're saying here is the length is equal to 100 take away the width, or 100 take away x. That's how they get that. Yep. Once you've identified that the width is 100 take away x, again, to get the area, hopefully you realize it's length times width. It's going to be 100 take away x multiplied by the other one multiplied by x. Yep. Expanding that out, the area is 100x take away x squared. So again, in this particular case, they're wanting you to find the maximum area. So again, that's going to occur when you differentiate the area. So dA dx, and you make it equal to 0. So doing that, in this particular case, it implies that x is going to be equal to 50. So this being equal to 0, x has to be equal to 50. Again, you can check here and check the gradient chart. Stationary point, checking what's happening to the left. Okay, it's a positive gradient. Checking what's happening to the right. It's a negative gradient. When it goes up and then down, obviously that is going to be a maximum. So check that. And once you've identified that that is going to be a maximum when x equals 50, you can actually find out what the dimensions will be of that maximum area by plugging this back into the area formula. So 50 multiplied by 100 take away 50, or 50 times 50, is 2,500 meters squared. Cool. Next one here, it says here two variables x and y are such that x to the power of 4 multiplied by y equals 8. And it says we've got a third variable, z is defined by this here. It says find the values of x and y that give z a stationary value and show that this value of z is a minimum. Cool. It says here obtain y in terms of x from the equation here. So to do that, obviously what we're doing is we're dividing this side by x to the power of 4. Come on, pen. X to the power of 4. Anyway, we divide this side by x to the power of 4. You divide this side by x to the power of 4. It's not liking it, is it? X to the power of 4. Now, obviously, if you've got 8, or y equals 8 over x to the power of 4, remember that can be rewritten back up on the top line as 8 x to the power of negative 4. which is what they've done here. In this particular case, it says then we're going to substitute this into the equation, z equals x plus y. So where the y is, we've just substituted in 8x to the power of negative 4. It says now z is expressed in terms of one variable. We can differentiate with respect to x. So here we can differentiate this, and we get dz dx is equal to 1 take away 32x to the power of negative 5. Now again, what we're showing here is a stationary point occurs when the derivative is equal to 0. So let's make that derivative equal to 0. Rearranging things, we get x equals 2. It says there is a stationary point at x equals 2. Its corresponding value of y, you can just substitute that back into one of the original equations, and we can find out it's 1/2. From there, you've got y and you've got x. You can substitute those in equation 1 to find z. So we're plugging these back in, and you can get z. It says here, determine the nature of the stationary point by using a gradient chart. So again, we've got x equals 2 is the stationary point that we discovered before. Looking at what's happening to the left, look at what's happening to the right. To the left, obviously it's got a negative gradient, and to the right it's got a positive gradient. So when it goes in this type of shape here, it's obviously the stationary point is at a minimum. So we can verify that. So we say the minimum value of z is 2.5, and it occurs when x equals 2 and y equals 1/2. I want to have a look at example 30 as well. And example 30 says the following. It says assume that a number of bacteria are present in a culture at a time t is given by n of t, where we've got this equation here. At what time will the population be a maximum? It says find the maximum population. So we've got the equation nt. We're going to differentiate that. So n dash t we've got here. We can take out e to the power of negative 0.1 t as a common factor, as we can see, it's pulled out the front there. Now, obviously, to find out what's going on, we need to with the stationary points. We need to make the derivative equal to 0. When this is equal to 0, either this part has to equal 0 or this part has to equal 0. Obviously, for this part to equal 0, it implies that time has to be equal to 10, because 3.6 times 10 is obviously 36. 36 take away 36 is the 0. Yeah. So we've discovered it implies t equals 10. What you can then do is plug that into the original equation and find out what the maximum volume is. So n, when we substitute in 10, is 360 e to the power of negative 1, which is approximately 132. Please have a look through the other worked examples. There's a fair bit going on there. Have fun with this exercise. Bye for now.